Welcome to qnawire.
In this problem, we are learning how the derivative, or the first and second derivative, affect the shape of the graph. More specifically, we're going to be using the first and derivative test to determine things like the intervals of increase and decrease and the concavity of a function. So for part A, we're given the function f of x equals x times the square root of 6 minus x. So the first thing that we'll do is we'll take the derivative, right? We're trying to find the intervals of increase and decrease. So your mind should be thinking, I need to take a derivative. So we'll take f prime of x, and we'll have to use the product rule here. And then once we simplify the product rule, we'll get f prime of x equals 12 minus 3x all over 2 times the square root of 6 minus x. And then remember, we want the critical numbers. Now this might be a little bit tricky because we have this fraction as our derivative. Well, remember that if the numerator of a fraction is 0, then my whole fraction is 0. So we can set the numerator equal to 0 to find the critical numbers. So we'll set 0 equal to 12 minus 3x. We'll solve for x. X is 4. So now we can find the intervals of increase and decrease for our function. The domain of our function is from -infinity to 6, and our function does include 6. So our first interval would be from -infinity to 4 to our critical number. And then what you can do is you can pick a number in this interval. You could plug in 2, for example, and then you can plug it into our function and determine the sign of that function. And when you do that, we'll find that it is positive, so it is increasing. And then our second interval is from 4 to 6, and you'll find that our function is decreasing there. And now for B, we're told, let's find the local maximums and minimums. Well, from the first derivative test and the sign of the function that we just found, we have a local maximum when x equals 4. So you can plug in 4 into the function to get f of 4 equals 4 times the square root of 2. So the point at which we have a local maximum is 4, 4 square root 2. Now for part C, we're told to find the concavity of the function. Now when you hear the word concavity, your mind should go to second derivative. We need the second derivative test to determine concavity. So we'll take the second derivative. Now you might be looking at the first derivative and think that's a tricky derivative, and you're right. You have to apply both the chain and the quotient rule. And then once you do that, f double prime of x equals 3 times x minus 8 all over 4 times 6 minus x raised to the 3/2. And then what we can see in this function is that our second derivative is less than 0 for all x in our interval -infinity to 6. So that means that our function is concave down when x is in that interval. And now for D, we're told, well, is our calculus correct? Can we compare it to a graph and say that what we found matched the graph of the function? And this is the graph of the function. You can see that we got it correct. We have a local maximum here. We don't have any points of inflection. Our concavity matches, so we did well. So I hope that this problem helped you understand a little bit more about how the derivative affects the shape of the graph, and specifically how we can use the first and second derivative to determine things like the interval of increase and decrease, local maximums and minimums, and concavity of a function.